Welcome to an interactive course designed to test and improve our knowledge of heat treatment. The topic of this section is to explain the issues of tempering, both under a protective atmosphere and in a vacuum. Before we start the actual tempering, let's go back to the theory. The picture shows a binary diagram of iron-iron carbide, which shows phase transformations in steel with different carbon contents. However, since after quenching, we have a martensitic microstructure that we need to temper, we will not find this structure here. This diagram only shows structural components that are formed during slow heating or cooling. Martensite is a structure that is formed during rapid cooling of steel from the austenitization temperature, and if we want to know how it behaves, we have to go to the so-called CCT diagram. From the diagram shown, it can only be seen that the original austenite phase cools quickly through the A3 or ACM transformation line. But there is not enough time for the austenite to transform into the mentioned structural components, such as ferrite, pearlite, or cementite. A continuous cooling transformation CCT diagram is a graph used in materials science and heat treatment, particularly for steels, that shows the phases and microstructures formed when a material is cooled continuously at various rates from a austenitizing temperature. As already mentioned, the goal of quenching is martensite. Martensite is a supersaturated solid solution of carbon in alpha iron in ferrite. Due to the rate of cooling, therefore, austenite is not transformed into ferrite and cementite, or a combination of these, but a structure called martensite is formed. Because the excess carbon is enclosed in the ferrite lattice, this structure has a high internal stress precisely because the carbon occupies otherwise free interstitial positions in the lattice. In the event that we cool more slowly, a structure called bainite is formed, and in the case that the cooling is even slower, we get into the area of pearlite. Since carbon can only move in steel by diffusion processes, the transformation of martensite into other structural components at low room temperatures would be very slow. Therefore, it is necessary to reheat the material and accelerate these diffusion processes. By reheating to a temperature below A1 for tempering, martensite gradually transforms into structural components depending on the carbon content. In all cases, the result of this process is lower hardness, and at the same time, higher toughness and ductility of steel, the properties we need in steel parts. When we start with tempering, it is necessary to take into account that not all austenite is transformed to martensite. Depending on steel alloying, a certain amount of so-called residual austenite almost always remains in steel. Its amount should not exceed 10%, but there are steels where there is much more of it. An example is this diagram, where it can be seen that the steel has the martensite finish curve shifted to negative temperature values, and therefore with standard quenching into a quenching medium with room temperature or higher, full transformation of austenite will never be achieved. To complete the martensitic transformation, it would therefore be necessary to go to negative temperatures. That is why sometimes on the CCT diagram, in addition to the martensite start line, you can also see data such as martensite 50% or martensite 90%, telling you what percentage of austenite is transformed into martensite, and the rest is just residual austenite. This must then be taken into account both when determining the cooling procedure and subsequent tempering. During tempering, structural changes occur in the steel, which fundamentally affect the resulting hardness and other mechanical properties. The individual phases can be described as follows. In the first phase, at temperatures of 100 to 250 degrees Celsius, there is a gradual release of carbon from the supersaturated unstable martensite. This released carbon transforms into non-equilibrium iron epsilon carbides. At this stage, there may be a slight increase in hardness. Oversaturated martensite becomes low-carbon martensite, and it is the increased content of epsilon carbides that can increase the hardness. The second phase takes place between temperatures of 250 and 350 Celsius. In this phase, residual austenite breaks down, which can be in large quantities in the matrix. Due to the increased temperature, diffusion processes are accelerated, and under this, the residual austenite transforms into untempered martensite, which subsequently into ferrite and iron carbides. At the same time, internal stresses are released, and the hardness of the steel decreases. The third phase starts at 300 Celsius. In this phase, low-carbon martensite releases the remaining excess carbon, and a complete ferritic carbide structure is formed by ferrite and needle-like or plate-like cementite, with the gradual decay of epsilon carbides. The result is a softer matrix with increased toughness. If steel contains carbide elements such as chromium, molybdenum, vanadium, tungsten, titanium, and niobium, up to a temperature of 400 Celsius, these carbides are very stable. Above this temperature, however, their amount and volume begin to increase at the expense of cementite formation. A secondary hardness effect is created. This is the fourth stage of tempering. Elements that do not form these carbides, such as manganese, silicon, nickel, do not affect this tempering phase. In the last, fifth phase, carbon diffusion is accelerated, cementite particles increase further, and, as a result, hardness decreases. Structural changes during martensite tempering depend not only on temperature, but also on time. If we want to achieve a defined hardness, we can do it in different ways. Either at lower temperatures and with a longer time, or at higher temperatures and in a shorter time. However, you cannot work with these variables indefinitely. As a rule, we will achieve better results at a lower temperature and longer time than vice versa. For low-alloy steels, it should be at least 1 hour at temperature. For high-alloy steels, it should be 2 hours. If we use classic diagrams with tempering curves, it is important that it is always stated under what conditions the hardness was achieved. Otherwise, it is only indicative information, and we have to verify it under our conditions used in our heat treatment plant. If tempering were carried out at a constant temperature for a very long time, then the individual stages of the breakdown of the supersaturated martensite structure would proceed in the timeline as shown on the screen, in the same way as if we were increasing the temperature. Some phenomena will occur immediately, and some phenomena will occur gradually, as diffusion processes and carbon migration will take place in the steel. It can be clearly seen here that some processes will occur weeks or months, often only after several years. These are similar phenomena to those known from precipitation, annealing, or aging of steels. They cannot be prevented, but on the contrary, they can be accelerated by increased temperature during tempering. If we summarize and simplify all the above, the tempering process has two basic goals: to reduce the stress in the material by tempering martensite to the required hardness, and to ensure the transformation of residual austenite to martensite, both for stabilizing the structure and the dimensions. It is important for the work of the heat treatment plant that the tempering operation is reproducible. Therefore, it is necessary to correctly define the tempering holding time in the operating conditions and fix it as a mandatory parameter for determining the tempering temperature to achieve the required hardness or strength. For devices that can work with a core thermocouple TC, the advantage is the possibility of automating the tempering cycle, meaning the temperature holding time, regardless of the size and weight of the product being tempered. This temperature holding time is calculated from the moment when TC reaches a temperature difference, for example, 15 Celsius from the required furnace temperature and should last at least 2 hours for tool steels and at least 1 hour for other steel grades. The parameter delta T is at the heat treater, but if it is determined, it must be used for a long time to ensure the reproducibility of the results. The resulting hardness depends not only on temperature, but also on time, and changing the delta T parameter means a significant intervention in both the tempering holding time and the resulting hardness. On the other hand, systematically fixing the tempering parameters in the furnace program allows for subsequent statistical evaluation of hardness results and establishing your own tempering curves, valid only for a given furnace and for a given delta T parameter. If the heat treater adopts this method of tempering, then the probability of achieving the required hardness, regardless of the size of the part, is greater than 95%. There are many types of tempering furnaces where we cannot use any core or surface load thermocouples. The reasons are various. Usually, it is the mobility of the batch or loading into the hot chamber. In that case, as with quenching in a protective atmosphere, we can use this graph for cycle modeling. This consists of the heating phase, heating through the full batch and parts, and holding at tempering temperature. Holding at temperature is defined by the tempering time and, as already mentioned, is usually 1 to 2 hours. The heating time is the time from the loading of the batch into the hot chamber until the surface of the batch reaches the temperature of the furnace. However, we do not have full control over this phase. We only see the moment when the furnace was heated to the required temperature, set point, but we do not have any information about the batch and its surface and core temperatures. If we temper above 500 degrees Celsius, then, theoretically, the surface of the batch already emits visible dark red light, and if we have a viewing window into the furnace, we can control this moment. However, we usually do not have such an opportunity. So we are left with the heating step, when the surface of the batch is already heated to the required temperature, set point, and now we just have to thermally homogenize the part and the batch in full profile. For simple orientation, we can estimate the time depending on the diameter of the parts using a table or graph, or we can use another determination of this step based on our experience, respecting long-term statistical monitoring of tempering results. However, this diagram is valid for one part of a specific size, but to correctly determine the time, we must also take into account the composition of the batch and positioning of components. In any case, the heating phase of the entire batch, marked in green, is not under our direct control, and therefore we must help ourselves by reproducing the previously used process parameters, when the hardness result corresponded to the conditions of the assignment. Our next task is to determine the number of temperings. This varies depending on the steel grade and the application. Although there are processes where tempering is not performed at all, a minimum of 1 tempering is required for standard quenching processes. For steels or processes where a large amount of residual austenite can be expected, 2 temperings are recommended, and in cases where maximum mechanical properties and dimensional stability are required, 3 temperings are recommended. The reason is as follows. After hardening, the core of large parts can contain more than 30% of residual austenite, which is an austenite that has not yet been transformed into martensite. The remaining part is untempered martensite. After the first tempering, only the martensite formed during the quenching cycle is tempered. At the same time, however, as the residual austenite continues to decompose, new untempered martensite is formed. The structure would therefore consist of once tempered martensite, untempered martensite, and residual austenite. Only with the second tempering is the first part of the martensite tempered twice, and the second only once. This may be sufficient for some applications, But where there is a requirement for maximum mechanical properties and dimensional stability, a third tempering must be included, which ensures that the majority of the martensite is tempered at least twice. In the previous section, we determined the tempering time and the number of tempering cycles. We now need to determine the temperature. In order to properly perform the tempering process of steel, we need to know its tempering curve. This is another diagram that is developed and known for each steel. It is usually in the form shown in the figure, where the dependence of the decrease in hardness on the tempering temperature for defined times is shown. However, we cannot trust such a diagram without limits, especially if there is no information about the conditions under which the quenching and tempering were carried out. This example is for steel 1.2842. The typical hardness for this material is 58 to 62 HRC. According to the selected hardness on the vertical axis, we find the corresponding tempering temperature, approximately 200 degrees Celsius. In this case, we are dealing with tempering 42 chromium molybdenum 4 steel, a steel used for common structural parts and intended for quenching and tempering in multi-purpose furnaces. We need to temper the material to strength of 1,300 megapascals. In the diagram, we find the strength on the vertical axis and the temperature on the horizontal axis. The parts must be tempered at 550 degrees Celsius. This tempering diagram is for hot work steel type H13, 1.2344, and also shows the portion of retained austenite in the steel and the tempering brittleness area. The diagram was prepared for 2 temperings, each with a holding time of 2 hours at the tempering temperature. Both data must be taken into account. The amount of retained austenite shows how much volume of austenite remains in the structure without transformation to martensite. Steel with such a portion of retained austenite will be unstable, because even at room temperature, the retained austenite will tend to transform to martensite by diffusion processes, although this may take days or weeks. However, since martensite has a larger volume than austenite, the steel will change dimensions, which can be a problem with hundredth tolerances, and at the same time, it will be loaded with high internal stresses precisely because of this change in volume. Therefore, such steel should be tempered at high temperatures, ensuring full transformation of the retained austenite. The secondary hardness region indicates that significant precipitation of alloying element carbides occurs in the steel at these temperatures. The external manifestation of this phenomenon is an increase in hardness. In terms of mechanical properties, this region is characterized by increased brittleness and reduced ductility. For the use of steel with such a tempering diagram, this region should also be excluded. Therefore, the lowest tempering temperature should be at least 565 degrees Celsius and more. This is very important for steels for hot work, since both retained austenite and secondary carbides reduce toughness and increase the susceptibility of the steel to thermal fatigue cracks. If we cannot find the tempering curve for a given steel, there is a very useful tool from Ovaco. We can try it right away. If you click on this link, you will be taken to a table where you can enter your chemical composition of the steel. We will try our already mentioned materials. We will start with 1.2842 steel. We enter the chemical composition and click on Calculate. The application will calculate the dependence of the change in hardness on temperature, the curves for the tensile strength and yield strength, a simplified CCT diagram, and Jominy hardenability curves for hardening in oil, in water, and in air. The same procedure will be for 42 chromium molybdenum 4 steel, or for H13 or 1.2344 steel. The application gives us the option of entering either standardized average values of the content of individual alloying elements or directly entering the values that we have measured, for example, with a hand X-ray spectrometer. In that case, we will get values corresponding directly to the chemical composition of the steel that we have available. The calculation results are in good agreement with published data for the given material and are sufficient for basic orientation in hardening and tempering. However, if we are going to temper, it is good to think about the so-called rule of caution. This rule says that if the result is not completely verified, it is better to start at a lower tempering temperature so that the hardness does not fall below the required value. In that case, we would either have to ask the customer for an exception from the required parameters or re-harden the parts. However, re-hardening the material carries certain risks, and we should avoid them. However, it is also necessary to take into account that if the hardness does not work out, and we include additional tempering at the same temperature to which the part was tempered in the previous cycle, the hardness will still decrease by half to 1 Rockwell. This is a consequence of the fact that the resulting hardness depends not only on temperature, but also on time, and in this way we have essentially doubled the time at temperature. So again, the rule of caution should apply, and to fine-tune the hardness, we must increase the temperatures very carefully, preferably less than more. Tempering furnaces comes in various forms. They can be without a protective atmosphere, or they can work with nitrogen, argon, endo, or exo atmosphere. There are many options. However, the important goal is correct and reproducible tempering of parts, while at the same time preventing oxidation by oxygen or water vapor contained in the air, or avoiding surface decarburization by air. Atmospheres for tempering are mainly neutral. In some cases, they are intended for reducing of oxygen or water vapor in hot zone. A typical example are retort tempering furnaces with indirect heating from companies such as Ipsen, IVA, KGO, Borel, or Seco Warwick. Their principle is based on the fact that the batch is loaded into retort, not heated directly, but through a flow of protective atmosphere. The classic retort furnace design is based on supplying gas to the furnace with an overpressure slightly higher than atmospheric pressure. Usually, it is 30 to 50 millibar. This overpressure ensures that no outside air enters the furnace. At the outlet, there is either an expansion valve or a flame curtain, which prevent air from entering the furnace. Retort furnaces can also be evacuated, which means that the oxygen and water vapor content in the retort is significantly reduced before the actual process. In this furnace concept, the batch is heated from the outside of the retort, either by electric or gas heating. The tempering atmosphere, usually nitrogen, is heated and blown into the furnace via a fan to heat the batch. There is therefore the effect of heat radiation from the surface of the retort and at the same time convection heating from the flowing gas. However, in order for the furnace to cool sufficiently quickly, it is equipped with another fan and gas cooler, which ensure the cooling of both the batch and the retort in an acceptable time. Retort furnaces are advantageously used primarily for nitriding and nitrocarburizing. This type of furnace is also offered for tempering too. Its disadvantage is that it is necessary to heat and cool the retort in each cycle, and therefore its energy consumption will be higher than in furnaces specifically designed for tempering. The retort can weigh up to 1 ton, and if parts weighing 200 kilograms are tempered in it, most of the energy input is wasted. The second possible solution are vacuum tempering furnaces. Vacuum can therefore also be the basic working protective atmosphere. This is used in special processes such as annealing of light metals, titanium alloys, or superalloys for the aerospace industry. Usually, however, the vacuum is only an auxiliary tool that cleans and desorbs the furnace, and then the working atmosphere is filled into the furnace for the actual operation, tempering or annealing. Its pressure is usually from 0.8 bar to 1.5 bar overpressure. The higher the pressure, the better the heat transfer between the gas and the batch. The protective atmosphere here is mainly nitrogen and argon. Examples are tempering and annealing furnaces from the French company Fors BM1 or from the Polish Sikowarek, Italian TAV vacuum furnaces or Miup Forni. The concept of classic vacuum furnaces allows, unlike retort furnaces, direct heating of the batch. The heating elements are located in the inner working space with heat radiation directly to the parts. At the same time, the forced flow of the atmosphere allows for efficient convective heat transfer between the heating elements and the batch, making these furnaces ideal for tempering. They are efficient and very precise in terms of heating with high reproducibility of the result. Although both types of equipment are equivalent in terms of results, the concept of retort furnaces means that with each tempering cycle, a retort weighing hundreds of kilograms is also heated and cooled. In order for both types of equipment to achieve the same times in terms of effective tempering time, retort equipment must have a much higher power input. If we convert this to the power input required to process 1 kilogram of steel, then this difference is reflected in higher energy consumption for retort equipment, by more than 30%. For this reason, it is more advantageous to use retort furnaces for nitriding or nitrocarburizing, because for longer processes, the difference in energy requirements gradually decreases. So if we want to use retort furnaces only for tempering, we must also make an energy assessment of what such a decision will cost us, and what impact it will have on ESG reporting and our carbon footprint. If we need a furnace for combined tempering, annealing, and nitriding or nitrocarburizing processes, it is more appropriate to choose a device with low-pressure nitriding technology. We will retain the energy advantages of direct heating, and at the same time we can nitride with high quality. Another type of tempering equipment are furnaces, usually operated in a production line together with multi-purpose hardening ovens. For the construction of this type of equipment, the usual limit for the use of a protective atmosphere is 450 degrees Celsius. Above this temperature, the surface of the parts can be fundamentally affected by oxidation processes, and therefore it is recommended to use the endo or nitrogen protective atmosphere, depending on the purpose of processing and depending on the source of the atmosphere available. Heating elements, electric or gas, as in retort furnaces, are placed outside the work area, where they heat the protective atmosphere, and this heat is then transferred to the working chamber and to the batch by a fan. Since the furnace lining is usually oxidation resistant, these furnaces can be kept at a permanent temperature even without a protective atmosphere. The batch is usually placed in a heated furnace. Unlike the above-mentioned concepts of vacuum-sealable furnaces, which are always cold-loaded, this type of furnace cannot use load thermocouples to measure the part's temperature. The upper limit of the serviceability of tempering furnaces without distinction is usually designed at 750 degrees Celsius. In order for the atmosphere to actually prevent oxidation, it needs to contain a certain amount of hydrogen, which is able to bind to residual oxygen or water vapor and at the same time reduce oxides. When using pure gases such as nitrogen or argon, the oxidizing ability of the atmosphere is significantly reduced, but residual oxygen or water vapor is enough to discolor the parts from the oxides that form. The reactions between metal and oxygen are shown in the figure. In order to prevent oxidation at 400 degrees Celsius, oxygen partial pressure must be lower than 10-9 millibars. At a temperature of 900 degrees Celsius, even a partial pressure of 10-5 millibars of oxygen is capable of oxidative reactions with alloying elements in steel, like with chromium, manganese, silicon, and others. The same applies to water vapor. The dew point for 400 degrees Celsius should be -60, for 900 degrees Celsius up to -80, representing water partial pressure less than 10⁻⁶ millibars. The sensitivity of the atmosphere to oxygen or water vapor is therefore significant. In the past, tempering was commonly done according to interference oxide colors. The picture shows, for example, a table of oxide tempering colors published in the past by the steelworks. Today, this method of determining the tempering temperature is no longer used much, but it can still be seen, for example, in the work of artistic blacksmiths or knife makers. Protective atmospheres also have their pitfalls. For example, by comparing the endo-atmosphere and a mixture of nitrogen plus 5% hydrogen, we see that the endo-atmosphere creates a larger amount of carbides or carbonitrides of iron and alloying elements compared to a nitrogen-hydrogen atmosphere. The material will be more brittle after using the endo-atmosphere with a higher risk of breakage. Of course, the process temperature must also be taken into account. However, we must realize that many processes take place above temperatures of 500 degrees Celsius, which is already the temperature commonly used for nitriding or nitrocarburizing. It can therefore be rightly assumed that oxygen diffusion will proceed identically, like nitrogen or carbon. If we omit tempering in air, then the basic protective atmosphere will be nitrogen. There is usually enough of this in every heat treatment plant. The screen shows a typical gas distribution scheme in the operation of heat treatment with vacuum furnaces. Liquid nitrogen is evaporated in the evaporator to gas and then stored in a gas storage. This usually has a pressure of 15 bar and more, so that the gas consumption in a 10-bar quenching furnace is covered while maintaining a sufficient volume of gas for further consumption. At the same time, in the second line, nitrogen is fed into a mixer, where it is mixed with 5% hydrogen and then stored in a separate booster. An atmosphere with 5% hydrogen has a sufficient reducing effect on oxygen and water vapor, and ensures perfect cleanliness of the surface of the tempered parts. However, it can also be used with advantage for recrystallization, annealing of stainless steels, which are highly sensitive to the presence of oxygen. Up to 5% hydrogen, the atmosphere is not explosive and is safe. If the heat treatment plant is also equipped with multi-purpose furnaces, then it usually also has a source of endo-atmosphere. It is used primarily for quenching, but it can also be used for tempering. The only condition is a safety burner inside the tempering furnace, ensuring that the atmosphere burns out in the event of its contact with air. Its composition provides primarily protection against decarburization, and at the same time partial protection against oxidation. However, there are also operational reasons for its use. Since the endo generator operates continuously, this atmosphere is available 7 days a week and 24 hours a day. Since the output of the endo generator can only be regulated to a limited extent, especially in older types, it is better to use the atmosphere for tempering than to burn it aimlessly. A typical gas installation on such a tempering furnace is shown in the picture. There is a supply for endo or for nitrogen, and the technologist can choose the type of atmosphere according to the application. There is also a supply of natural gas and air, but this installation is intended for gas burners that heat the furnace. The last type of atmosphere used for tempering is the exo-atmosphere of split ammonia. It has an excellent reducing ability to oxygen and water vapor, and is therefore preferably used for austenitic stainless steels, where there is a requirement for high surface cleanliness. In the heat treatment operation, there is usually no problem with ammonia. It is used for both nitriding or nitrocarburizing, as well as for carbonitriding. So if a ammonia cracker is added to the installation, the atmosphere is ready. Although it is explosive and highly flammable, when using retort furnaces with burnout at the outlet with retorts, there is no problem with either tightness or safety. This type of equipment and atmosphere has proven itself both for tempering small batches and for deoxidizing surfaces. The equipment usually works with two retorts, one in the furnace and the other on the cooling rack. Such a tempering equipment is therefore very operational and efficient, and the results in terms of surface cleanliness are extremely good. In order to properly temper, all of the listed devices must meet some basic criteria. First of all, we must be sure that the required temperature is the actual temperature. Therefore, all devices must meet the requirements of AMS 2750 for pyrometry or CQY9 for individual technologies listed in this specification. The table shows the classification of quenching and tempering furnaces for various activities and according to various standards. It can be seen that the requirements for tempering furnaces are usually higher than the requirements for quenching furnaces. This is logical because the austenitization temperature will affect the structural properties of the steel after quenching. But during tempering, we have the main requirement for hardness, and in this case, a large difference in the permissible tolerance of the temperature field would make a large difference in the resulting hardness. According to ISO 15787 standard, we should have ±4 Rockwell. But in practice, there is a common requirement for a narrower tolerance band of ±1 Rockwell, for example 45 + 2, 46 to 48, etc. Tempering furnaces should therefore meet at least the criterion of Class 4, which is ±10. Exact prescription you can find in CQY9 or AMS2 759 specs. This figure shows a theoretical example of how the furnace class can affect the resulting hardness. In this case, furnace class 5 gives a hardness variance of ±1 HRC, but it depends on the material being tempered and how steep the tempering curve is. Therefore, for lower tolerance band or other steels, the furnace class must be higher, 3 or 2, in order to fit into the hardness tolerance band. In order for a tempering or annealing furnace to be in a qualified condition, it must meet at least the following criteria. It must use only calibrated thermocouples according to AMS 2750, CQ19, and newly ISO 20431. Their calibration is carried out before being used on the equipment. The entire temperature chain must be periodically calibrated, which includes a temperature sensor, converter, recorder, controller, and display unit at a frequency according to the standard and according to the furnace class. SAT test, system accuracy test, must be performed once a 3 months, checking the temperature in the furnace using another thermocouple set aside for this purpose. TUS test, temperature uniformity test, should be provided at least once a year. Daily atmosphere control is required in the case of using an atmosphere with carbon. Gas analyzers should be checked once a week. Dew point measuring devices once a year, as well as meters for measuring the content of nitrogen, carbon, or oxygen in the atmosphere. Inspection and calibration of vacuum gauges should be performed once a year. Inspection and calibration of flow meters once a year. Inspection of the furnace tightness according to the application, usually but always before the first process that follows a process that has not been validated for aircraft production or special production. If the leak test fails, it is necessary to include a furnace burn-in. The temperature of the desorption cycle should be at least 50 degrees Celsius above the maximum technological temperature. Each furnace must be equipped with a calibration plan and a result on the accuracy of the temperature and its deviations. It is therefore a complex procedure, requiring high professional knowledge and a systematic approach. If this were not the case, the furnace should not work for either automotive industry applications or for the aerospace industry according to other standards. If the furnace is validated, released for the production process, we can start tempering. The configuration of the operation is varied, but usually hardening furnaces prevail over tempering furnaces. This is not optimal for the economy of tempering. We will show this on the example of vacuum processing, where the usual requirement today is double or triple tempering. We will process steels for hot work, where there will be more steel grades in one batch, and in addition, a different hardness will be required for each part. For this type of steel, double tempering can be considered standard. The table shows that some steels have a common criterion in the austenitization temperature, and therefore can be hardened in one batch. However, they also have a second criterion in common, which is the minimum tempering temperatures. For economical processing, it is therefore advantageous to harden them together in one mixed batch, and then temper them all at once, regardless of hardness, to the lowest permitted temperature. In our case, 565 to 570 degrees Celsius. Only for the second tempering do we sort the batch according to the hardness requirement and according to the tempering temperature for each steel in the batch, and tempering is carried out either in furnaces of similar dimensions or in smaller furnaces, more economically acceptable for smaller quantities. Since each cycle will last approximately 8 hours, the entire batch, 200 to 300 kilograms, can be effectively processed in this way within 24 hours, for hardening and 2 tempering cycles. This is very important. However, the condition is that the hardening and the first tempering take place in a furnace of the same dimensions. It follows that each hardening furnace should have at least one tempering furnace of the same size, but in practice, a ratio of 1 to 2 can be considered more advantageous. That is, at least 2 tempering furnaces should be available for one hardening furnace. This is the only way to ensure optimal service for the customer in terms of time, quality, and price. The second reason for the ratio of 1 quenching furnace and 2 tempering furnaces is the economics of the process itself. Usually, a tempering furnace is half the price of a quenching furnace. This also results in the costs per operating hour of the process. Tempering in a tempering furnace will therefore be significantly cheaper than in a quenching furnace. If we decide to temper in a quenching furnace, then we have chosen the most expensive possible processing. In addition, it is necessary to take into account that the energy consumption for the tempering process in a quenching furnace is much higher than in a tempering furnace. The reason is that a quenching furnace is adapted to heat transfer at high temperatures, while a tempering furnace is adapted to low temperatures. This factor will also affect the price of the process and the price for processing. The graph shows the relationship between processing costs and the number of tempering furnaces. The calculation is based on an hourly rate of 30 euros per hour for the quenching furnace and 15 euros per hour for the tempering furnace. The price decreases with increasing batch weight, but it decreases mainly with the number of tempering furnaces. The graph shows that the difference between the cost per kilogram of processing with 2 tempering furnaces and the complete process only in the quenching furnace is 50%. In other words, with 2 tempering furnaces, we save 50% of the processing costs. As we mentioned the group of steels for hot work and their processing in mixed batches, there are many more similar material groups. These include steels for hot forming, for forging, steels for plastic molds, steels for cold work, stainless steels, both martensitic and austenitic, or high-speed steels. It is only up to the ingenuity of the heat treater and its knowledge to optimize procedures and planning under conditions of custom heat treatment when the range of processing cannot be predicted in advance. Similar grouping can also be applied to multipurpose furnaces. For quenching, parts are grouped according to the quenching temperature and carbon potential, and after oil hardening and washing, they can then be tempered according to similar criteria. Since there is usually not enough capacity for tempering on multipurpose lines, the entire batch is immediately tempered at once, for example to 150 degrees Celsius, so that the hardness does not drop. And then, depending on the time available, it is then tempered to other temperatures. In practice, the permissible delay time between quenching and first tempering is a widely discussed question. The general rule is that this time should be as short as possible, for example, within 2 hours. However, there is no complete agreement on this parameter, and opinions differ. For example, the DMP-11 regulation for heat treatment of parts for the aerospace industry from Safran states that for high alloy steels, it should be as soon as possible, but no later than 24 hours. For low alloy steels, it should be within 24 hours for small cross-sections up to 5 millimeters, and within 8 hours for cross-sections thicker than 20 millimeters. However, this delay can also be technically parameterized in some cases. For example, when quenching large blocks for pressure casting, plastic or hot-formed molds, the piece is considered to be cooled when its surface temperature drops to 50 degrees Celsius. The reason is not the temperature of the piece itself, but the definition of the martensitic transformation, because the end line of martensite, which indicates the end of the transformation of austenite to martensite, lies below 100 degrees Celsius. Even if the insert is removed from the furnace at a temperature of Tc equals 100 degrees Celsius, as soon as the core temperature drops below this value, this does not mean that the transformation of austenite to martensite is complete. At this point, the core of a large insert can contain up to 50% residual austenite. Therefore, it is necessary to wait. For large inserts, this can take several hours. To define this delay, magnetically clamped thermometers are preferably used, which reliably show us the moment when the surface temperature reaches the desired value of 50 degrees Celsius. Only then can tempering begin. And why remove the insert from the furnace when the core temperature reaches 100 degrees Celsius? Large blocks cannot be cooled by forced gas or airflow because there is a risk of their rupture and destruction. This is the point at which the superposition of stresses from the temperature difference and the transformation of austenite to martensite occurs, and these stresses can exceed the material's ultimate strength. To avoid future disputes between all parties involved in the process about the effect of this delay between quenching and tempering, this transition must be defined and documented. However, since the hardened inserts are already outside the furnace, this phase of the process is not part of the quenching or tempering cycle record. Therefore, this situation must be documented in some other form, such as a photograph and a production process record, or a thermometer log entry that shows that the operator measured the surface temperature of the part on the cooling table with a magnetically clamped thermometer or other means, and that the temperature reached before placing it in the tempering furnace was indeed 50 degrees Celsius. The course of tempering is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.